Let's cover array indexing approaches. State-of-the-art ArrayDBMS index types fall into three categories. Cell value selection indices accelerate seeking cells whose values are in a given value range. For example, select cells with values greater or equal to 3. Compute indices accelerate computations on arrays. For example, compute a function, slightly tune its input parameters, and compute the same function again. Tune and compute again. So, hyperslabbing indices accelerate seeking cells in a given spatial range. They use relatively well-known data structures, so we're going to focus on the first two categories. Consider the following real-world example. The query is to find cells with wind speed greater than 20 meters per second. It's obvious that the resulting cells constitute only a small fraction of the array compared to the whole array volume. Hence, we should not perform full array scans when we answer such range queries. Bitmap indices utilize three main techniques: binning, encoding, and compression. Usually, bitmaps have good compression ratios. This makes them especially efficient. First, cell values undergo binning. In this example, a set of floating point values are divided into 3 bins. After that, bin numbers are encoded as bitmaps. Equality encoding creates a bitmap for each bin. The bit in a given position is set to 1 if the cell with this position in the original array has a value that belongs to the bin number associated with this bitmap. This equality encoding bitmap type is good for equality queries shown on the slide. You read only the bitmaps for certain bins and perform bitwise operations. Range encoding is well suited for one-sided range queries, while interval encoding is better for two-sided range queries. However, bitmap indexing has a drawback. You know that a chunk is an I/O unit. We need to read a chunk completely, which may be up to several megabytes, even if only a single cell contributes to the result. Integrated value index mitigates the aforementioned drawback. The array is still accessed in the granularity of chunks. However, each chunk contains subchunks. Consider the example on the slide. The array is divided into 6 by 6 chunks, and each chunk of 5 by 5 cells is further divided into half-open buckets with an interval of 1. For each bucket, a bitmap indicates the position of cells inside the chunk, while a segment of residuals keeps the trailing bits of the values. The index is optimized for both hyperslabbing and value-based queries. A query examines only chunks intersecting the query region and reads the whole chunk or just buckets in the queried value range. You need to create a full logical copy of the original data if you would like to use this indexing technique. The storage footprint, that is the percent of the uncompressed dataset, that is the last column, is always less than 100%. A peculiar feature is that chunks should be very large. For example, 64 megabytes in contrast to usual chunk sizes of 4 to 8 megabytes. In addition, indexing params for a given workload may be not straightforward to obtain. Let us look at a query example with a tunable function. As input, we take two large 2D arrays storing intensities of reflected solar radiation, near infrared spectrum and red spectrum. As output, we get a large 2D array, Soil Adjusted Vegetation Index, SAVI. SAVI aims to minimize soil brightness influences. It is special because it includes a tunable parameter whose value is not known in advance. We may tune L many times to find an appropriate value. In practice, SAVI can be used to predict crop yield according to the recent publication. However, we need to recalculate the crop yield each time we tune L. SAVI is not alone. Dozens of math functions with tunable parameters are used in practice. ArrayDBMSs answer queries with tunable functions as follows. For the first query, we get some L value and compute SAVI from scratch. Next, we slightly tune L and submit the SAVI query again. However, SAVI is computed from scratch again. This repeats for each subsequent query regardless of whether we computed SAVI before or not. In contrast, during the first query, Bitfun computes SAVI from scratch and creates an index. During the second query, Bitfun doesn't compute SAVI from scratch, but it uses the index to answer the query. Bitfun tackles an important class of queries not explicitly considered before in the context of ArrayDBMS, tunable queries. Bitfun explicitly focuses on the fact of tunability. Let me share some insights. Please have a look at the SAVI function. In general, it is rather a non-trivial function. However, we need only a particular piece of this function. Now, a natural question arises. How significantly does SAVI value change when recomputed for L equals L plus a small delta? Let's fix near and R values. The trick is that SAVI now becomes a function of only one variable. If we look even closer, we will notice that SAVI is close to a line in the vast majority of cases, that is, for most combinations of near and R values. Wondering what if the function is not a line? Please have a look at the paper for more details. The Bitfun approach from a bird's eye view looks as follows. The Bitfun index contains identifiers of simpler functions, approximating the given function with the required precision. Real data is not random, so the number of approximating functions is typically small. The indexes have good compression ratios. Bitfun can answer three query types, namely compute function values, evaluate inequality, and perform classification. Bitfun is integrated into ChronosDB. You can find more at the Bitfun homepage. Without Bitfun, you read two large arrays. With Bitfun, you read only one compressed array. This enables Bitfun to answer queries up to 8 times faster. Until recently, the research in array storage focused on persistent arrays. Recent research reveals that specialized formats for interim arrays like Bitfun or Compass can vastly reduce I/O and save CPU time. This research direction is very young. Please have a look at the publication years of the papers. Hence, many exciting opportunities are to be explored.